So we're going to pick up where we left off with solids. So last time we were talking about the basic shape that underlies the definition of volume is the cylinder, and it can look, it can be the ugly Quasimodo cylinder. And to figure out the volume of any solid, you need to put the x-axis somewhere, and you have a lot of freedom in terms of how to do that. And you need a function that gives you the area of a cross section through the solid in a plane perpendicular to the x-axis. So when you're at x high on the x-axis, the area of this, in this case it would be a circle, but you just need, this is the area of a slice function. And to figure out the volume is just the integral over all slices of a of x d of x. Okay, so we have a new source of solids. Last time we did like cones and spheres and things like that. But there's a way to get solids just from functions. So let's say that you have a little piece of a function here that is y equals f of x. And it's restrict between a and b, so we look at it on a closed interval and we can shade this thing. And now suppose that we spin it around a line. Like often we spin these things around the x-axis. So can you visualize what the solid swept out by this little sheet will look like? These things usually look like lamp shades or something, so it'll kind of look like that. And then there will be a little circle there. And this thing will look kind of like that, and then the back part of it will be circular. Okay, so this is a solid of revolution. And solids of revolution, they just come from rotating plane regions around lines. So rotate a region, which is usually the area under some curve, around a line, which is usually the x-axis. So one convenient thing about solids of revolution is that their cross sections are always just circles. So a typical cross section of this thing will just be a circle, and if you look at where that would be here, here's sort of the x that gave rise to that circle. So notice that this little green stick that I drew here, this is what becomes the radius of the circle. So this little, maybe green is hard to see, this little magenta stick is what becomes the radius of the circle. And what is that? That's f of x. Because that's just the distance from the x-axis to the curve is f of x. That's because that's how graphs work. So the radius of this thing is f of x, and so its area is equal to pi times f of x squared. And this is area as a function of x, so this is area of a slice function. So if you have a solid of revolution, its volume is very easy to compute, assuming that you can integrate x, because the volume is just the integral from a to b of pi f of x squared dx. So let's do an example. So this looks kind of like 1 over x. So let's suppose we have some axes, and here's a little bit of the function y equals 1 over x. Oh no, I have to turn the ruler off. So it looks kind of like that. And let's go between 1 and 2. So here's 1, and here's 2. This is y equals 1 over x. And we want to rotate this around the x-axis. And that makes the shape that we drew last time, kind of like this. And now we know from the formula that the answer, the area of this solid, or sorry, the volume of that solid, is just the integral from 1 to 2 of pi times 1 over x squared dx. So that's pi times x to the minus 1 over minus 1 from 1 to 2. So that's minus pi over 2 minus minus pi. So this is pi over 2. So the volume of this thing turns out to be pi over 2. All right. Okay, so let's go on to another page. All right. Let's see. So a couple things here. One is, what if there's a little bit of separation between the plane region that you're rotating and the line that you're rotating it around? So now suppose that it's annoying. Suppose that the curve that you're studying is right there, and then you're going to take this plane region, sort of bounded by two different curves. Just to make this a little bit more concrete, this top curve could be 1 over x plus 2. That could be the top curve. And this bottom curve could just be y equals 1. And let's pinch that off between 1 and 2, sort of like we did before. So here's 1 and here's 2. So now we're going to rotate this around the x-axis. So what does that look like? Notice it's a little bit different than it was before, you know, because it's going to be hollow on the inside. So it'll look kind of like this. And there will be a hollow part here, sort of a hole straight through the thing, like a soup bone. And there will be a soup bone hole all the way through. Okay, so hopefully you can visualize that, and you see why it's happening. So now the formula that we used before, the formula pi f of x squared dx, that doesn't exactly work anymore, because when there's a hole in the thing, the cross sections are not circles. If I take a cross section here, it's circular, but it's not a circle. It's a circle with a hole in it. This thing, if it thinks you drew a circle, it will make it perfect. There you go. All right, so it's like that. There's an outer circle and an inner circle. So where are the radii of these circles coming from? And the cross section is this stuff. I think we said in class before that this shape looks kind of like a pineapple slice. Is called an annulus. And if you want to compute the area of an annulus, it has a little radius and it has a big radius. And the area of this thing is just pi r squared minus pi little r squared. And that makes sense because it's the area of the big circle, take away the area of the little circle. So now let's see if we can figure out what that means in terms of these functions. So here I actually gave you two functions, but just so we can derive the rule as we go along, let's just say that this top one is equal to f of x, and this bottom one was equal to g of x. Then the little radius comes from this. The little radius comes from g of x. And the big radius comes from f of x. So in this situation here, r is just going to be f of x, so that's the function that's on top. The function that's on top makes the bigger circle. And the small radius is going to be g of x. That's the function that's on the bottom. The function that's on the bottom makes the smaller radius. Okay, so now the area of a slice at x for this kind of solid of revolution is pi f of x squared minus pi g of x squared. And so if I want the volume that comes from this kind of solid of revolution, then it's just the integral from a to b of pi f of x squared minus pi g of x squared. dx. All right. And we have some particular functions here that we could be using. So in our problem, f of x was equal to 1 over x plus 2, and g of x was the constant function 1, and a was 1 and b was 2. So for the thing that we set up, we have to take the integral of pi times 1 over x plus 2 minus pi, and then dx. So what is that? That's pi times, oh, this should be squared. I forgot to do the squares. Oh, that makes it annoying. That means I have to like do this on its own page. So let's do it. Let's go to the next page. All right, so this is the integral that we want to take to figure out the volume of our ham bone. And I'm going to multiply this stuff out. The integral from 1 to 2, I'll take all the pi's out here. So this becomes 1 over x squared plus 4 over x plus 4 minus 1 dx. You can skip ahead to the end of this integral if you find this boring. 1 over x squared plus 4 over x plus 3 dx equals pi times minus x to the minus 1 plus 4 times natural log the absolute value of x plus 3x from 1 to 2. And I'm too proud to do that arithmetic. It's just some number. Who cares what it is? All right. So this is what we just did is sometimes called the washer method, and that's because if you've ever put together something from IKEA, you know, it comes with these little metal things called washers. It's like a metal ring with a hole in the center. So what we just did is the washer method. What we had done previously when the disk is solid, we call this the disk method. So there's the washer method and the disk method. The disk method is just the same as the washer method when the hole in the middle is infinitely small. Okay. So that's a good place to stop. I'm going to stop the video here and let's take a break.